morning. My name is Romina Tapia, and the project is about a study of the mass transfer of the absorption process with ammonia water in plain heat exchanger for absorption refrigeration systems. The absorption cooling system has advantages such as energy and economic savings because the heat source can be obtained through solar or residual thermal energy, and the use of natural absorbent substance such as water. The absorption refrigeration cycle begins in the evaporator where the pure ammonia absorbs the heat from the refrigerated space, causing its evaporation to pass to the absorber in the gaseous state, where the water absorbs it. The ammonia water solution is pumped towards the generator where it is converted into the pure refrigerant vapor that enters the condenser and then the evaporator for the repetition of the cycle. In the bubble absorber, the water fills the interior of the central channel, while the ammonia vapor is injected in the form of bubbles in the heat dissipation is carried out with the help of cooling water. The objective of the project is to determine a predictive model of the final ammonia concentration based on mass balances and the double-layer theory of mass transfer for the development of the parametric studies in Python with respect to different independent variables of the case study. The project development begins with the determination of the boundary conditions of the double-layer theory, which are the initial concentration of the ammonia in the water at a height of the absorption column of 0 meters, and the ammonia concentration of the liquid phase in equilibrium with the gas phase at a height of 0.5 meters. Then the initial data of the base case is identified, and likewise the code is written in Python, so that the user can enter this data in a specific range. Third, the dimensionless numbers necessary for step 4 are calculated, which consist of determining the mass transfer coefficients through the appropriate correlation. Then the mass balance is proposed in order to obtain a predictive model of the final concentration of ammonia in water. And finally, with the help of Python, parametric study of the main independent variables are carried out. The results of the mass transfer coefficient was 19.88 kilomole per cubic meter. And the final concentration of ammonia in water for the base case was 0.058 meter per second. The result of the parametric study show that the base bubble diameter can be used is 0.5 millimeters with a system operating temperature of 303 kelvin, an absorption column weight of 0.75 meters. It should be noted that temperature and height were obtained through improvements in the variable determined by the parametric study prior to each one. The results show that the final concentration of ammonia in water increases only 1 kilomole per cubic meter. Therefore, it is necessary to analyze the parametric studies in order to find improvements. There is a direct relationship between the height of the absorption column and the final concentration of ammonia in water. This is because the higher the height, there is a longer residence time and greater contact. Therefore, the absorption will improve. On the contrary, there is an inverse relationship between the operating temperature and the final concentration of ammonia in water because the gases are very absorbed in liquid at low temperatures. An inverse relationship also exists between the bubble diameter and the final concentration of ammonia in water because having small bubbles affects the transfer area and there is more contact between the liquid and gas phases. Conclusions. The absorption of ammonia in water was bad in the base case study. This can cause problems in the generator of the cooling system because a very pure refrigerant vapor is required. The use of ambient operating temperature represents improvements in base case absorption. A bubble diameter less than 2 millimeters improves water absorption. Increasing the height of the column Increasing the height of the column improves the absorption process, but depends on the size of the heat exchanger. Thank you.